Good morning, everyone. My name is Vasily. As Dani represented, I'm a PhD student and one of the developers of Aiida FLEUR plugin, which is responsible for input-output data and calculations management for FLEUR code families. And during my presentation, I will cover only general ideas of my plugin, of our plugin, of course, and more detailed description will follow for the tutorials, which we'll have this afternoon. And during my presentation, I will cover 5 main topics. First of all, I'm basically going to repeat the main ideas of previous presentation. That's why it's good to use Aiida for your calculation management and for FLEUR calculations especially. Then we'll look into the structure of the plugin. First of all, we'll consider how Aiida works with data. Next, we'll move to the representation of calculations, of calculation process in Aiida. And finally, we'll look into the blockchains, which represent scripts and automatize certain tasks for Aiida. And in the end of my presentation, I will make you a small introduction to the tutorials that you have this afternoon. And yes, to begin with, let me show you some 3 most common problems that computational scientists can encounter. It's based on my personal experience. It depends on the person. Someone is better organized. Someone have a lot of problems. I would say that I'm not really organized person and do a lot of mistakes. And one of the most common mistake that I do is, as you see, I show you only a small part of imp.xml file. You're already familiar with this. And after a long, hard-working day, I need sometimes change 10 or 15 of this by hand. For example, for older versions that are not supported by Aiida. And as you see, it's easy to make a mistake. It's easy to make a misprint. I did it several times. I submitted some jobs that generated absolutely trash results only because I missed a dot and used not that number that I wanted to. So we need to automatize this stuff. So it cannot be done by hand. If you do it by hand, you do a mistake. That's common for a human being. The next most common issue is that people usually are too lazy to organize their data, and you end up with such a structure of your data. And again, in my experience, if you ask me what's inside my untitled folder 46, I will not be able to answer this. I need to investigate this for several minutes to understand what calculations did I do in this folder. And it's also true for the vice versa situation. Sometimes I need to remember what type of calculations did I do 4 months ago. I remember that I calculated magnetic anisotropy energy for a particular structure. I need to find this, and I cannot find this. So it should be solved. And finally, it's a more general problem, which concerns the communication between several people or between research groups, is that when ab initio calculations are published, it's usually only input data is given and results. They tend not to describe in detail exact processes they did do to achieve these results. They have some set of input parameters, cutoffs and k-point meshes, and results. It's hard to track the exact steps they did do to get a particular result. Yeah, it's a big issue. And luckily, all of these issues can be solved using Aiida interface, which first of all automatically manages your calculations, submissions, retrieval. It can automatically submit your calculations to the supercomputer, get them there, parse your output data, find and process necessary results. And more importantly, it writes all your steps, all your data, all your processes in the database. You will never lose this. It's automatically structured in a good way. You can always track what input data was used in which calculations produced what kind of data, if this data was used in other calculations. It's all of this recoverable. You just need to look into the database. And as Jens told you, files are not stored in the database. I would say we have only links in the database, and this physical input-output files such as input.xml and out.xml, for example, they are stored in the repository, which is, I would say, inseparable from the database, but a little bit different thing. And however, to make Aiida working with your code, with the code of your interest, for example, FLEUR code, one needs to teach Aiida to do this because all the codes are different. WASP requires its input files and generates its output files. FLEUR is different, so we need to develop an additional plugin on top of Aiida for each code. And in our research group, we develop Aiida FLEUR plugin, which can be split into 3 main parts. So we need to take care of 3 main issues to develop a plugin. First of all, we need to teach Aiida how to manage data. We need to teach Aiida what's input.xml file, what is out.xml file, how to generate them. modifier object which contains an imp.xml file to modify, and the list of changes that you want to apply on top of this imp.xml file. And if you want to fix this, if you want to produce an imp.xml file that contains all these changes, you just need to call a special method that generates a new FLEUR imp data object. So to sum up this slide, you will have two FLEUR imp data objects. The first one is an original one, and the second one a modified one. So we will consider this in more detail during the tutorial. And now let me consider registration methods in more detail. So as you already know, that imp.xml file is an XML file. So it sounds silly, but it's true. So what can you do? How to modify this file? It's basically a set of tags and its attributes. So any value corresponds to a certain key. And as any XML file, you can basically change, delete, replace, or create a new tag. And for this, we have, I would say, two types of methods. The first one is called XML methods. For this, you need to pass the full path of an attribute that you want to change. For example, if you want to change the total number of iterations that FLEUR does, you need to know where it is located, where the itmax is located. It will not work if you make a mistake in this path. However, itmax attribute is always located. You can find this only on this path. So it's fixed somehow. So we have a set of simplified changes, shortcuts that already know where to find this attribute. For example, again, if you want to change the total number of iterations, it's enough for you to pass only the total number of iterations key. And it will automatically find this path and call this function, basically. And we have also more example of this comparison between more complicated XML methods and their shortcuts. For example, we can change species parameters. A good example is a muffin tin radius. Yeah, as you see, again, a shortcut is much easier to use. You don't need to know the exact path of the muffin tin radii. And it's also true for atom group attributes. And as you see, XML methods can be more flexible, but really not convenient, because one needs to remember exact path where to find a certain value and attribute. And shortcuts, I suggest using shortcuts, but sometimes they're not flexible. Not all the attributes are supported. If you want to change some attribute that it's not common, for example, it's not supported. Yeah, this slide is the end of the data section, and now we continue to the calculation. How INPGAN and FLEUR calculations are represented in Aiida. But first, let me add 3 more Aiida types that represent engine. So we also need to store all the information about the executables we have, about a certain process that we had, and the blockchain. And we have 3 more classes for this. First of all, it's a code class, which represents an executable. So in our database, we will have a code instance that represents compiled FLEUR version, for example, FLEUR MPI. We also can store the process of an execution. For example, if you want to run a single FLEUR calculation for a certain system, this process of execution will be stored in the database as a calc job instance. And finally, there is a blockchain instance that represents a chain of process, a script, a more complex algorithm. It connects several calc jobs in one, let's say, group, which unifies them. And using these data types in the database, we can store them and work with them. And I will not look into the detail how to execute input generator and FLEUR code. We'll again consider this in more detail during the tutorials, but the simplest scheme that can represent the in-begin calculation is that you need to pass to the instance that represent in-begin calculation a structure, which is a structure data node, calculation parameters. These are parameters that will be written into the simplified input and in-begin code itself, to the instance which represents in-begin calculation, this calc job. It will run, store a calc job instance in the database, remember all the outputs, inputs and outputs, produce a single FLEUR input data object which represents input.xml file, and will parse it. It's, in some sense, it's similar to what you did by hand. So first of all, you generated a simplified input for the input generator. You wrote structure in the first part of this file. You wrote some parameters to the second part of this file. You executed input generator, and you produced an input.xml file, which is FLEUR input data in Aiida. And FLEUR calculation have basically the same structure. We can reuse, for example, input.xml file FLEUR input data in the FLEUR calculation. We can pass a charge density from the previous calculation to run a FLEUR calculation. We need to pass the code. Again, we execute FLEUR, and we get some input and output parameters in the database, which are the most important one. I would say it's a parsed out.xml file, so you can get an easy access to the output parameters. Let me show you it on the next slide. Yes, that's basically the parsed result of the input generator and FLEUR code. As you see, input.xml file is parsed into the convenient Python dictionary, and you can easily get access to any parameter written into the input.xml file. And out.xml file, which is a result of FLEUR calculation, is also parsed. You can get access to any parameter that you might need from the FLEUR calculation. For example, you probably need the total energy from any calculation, and you can just access this via energy and energy units key in the dictionary. And yeah, and in the next part of my talk, I will continue with the blockchains. As I told you, blockchains represent more complex algorithms to get a particular result, and yeah, it performs a chain of calculations, and a node that represents a blockchain connects several calculations in one sequence, which can be tracked. A good example is an equation of states, where you, for example, need to calculate energies of a set of the same scaled structures. For example, you need to find an energy of structure which is a little bit shrinked and a structure which is enlarged, and to plot the energy against volume plot. And you can imagine how to do it by hand. You need to manually submit at least 5 FLEUR calculations, scale it by hand. It can be done, but it's not convenient, and it can be easily automatized. And in Aiida FLEUR plugin, we have equation of states blockchain, which basically behaves itself like a calculation. You need to pass a set of inputs. In this case, that would be an original structure, a set of input parameters, which contains, for example, the scaling parameters and other important parameters for the simulation. It will automatically process a set of calculations. It will run calculation for this structure, this one, this one, this one, and this one. And later, it can be processed, and we can get this a nice plot with basically no effort. It will be done automatically. Everything that you need to pass is basically the original structure with the scaling parameter 1.0, which is in the middle, pass the all wanted scaling parameters, some other parameters that you might need, it depends. And yeah, you will get the result. And one of the main blockchains in the Aiida FLEUR is the self-consistent blockchain. It's responsible for converging the charge density. Jens showed you an example how he used this blockchain to study a lot of structures. And this blockchain is basically submits several FLEUR calculations to ensure that your charge density is converged. And how does it work? First of all, it submits input generator if it's needed to generate an input for the FLEUR code. Let me know that this IntGen is not run always. It depends on the setup of the inputs. It's not necessary to pass structure and FLEUR int data to the self-consistent blockchain. You need to just pass structure or FLEUR input data, and it will automatically decide if you need to run input generator code or not. And then it will apply some modifications to the input.xml because a user can apply them. There is a certain key in the input parameters, and it checks the convergence. Yeah, it will not be converged on the first step, and it will run a FLEUR calculation. Run a FLEUR calculation. Then it checks, after this FLEUR calculation, then it checks if the charge density was converged again and submits the next FLEUR calculation, and it submits it until charge density is converged or until the maximum amount of tries is exceeded. And I also want to emphasize that we have not only density convergence mode, but we can also converge energy or the largest force of the structure. Sometimes you're not interested in charge density. Sometimes you want to make sure that your forces are converged or total energy. So we can track also these values. And what is the output of the self-consistent blockchain? They are also parsed into the dictionary. You can access the most interesting that you might need parameters. It's usually a list of charge densities, distance, and total energy. So you can use them, or better, use already written plot FLEUR method that automatically fetches, analyzes this output, and plots distance against the number of iteration. And as you see in this example, this calculation was able to converge the charge density to the 10 in -5. It's not a great result, but I could continue this. It's just a test. And The main advantage in using blockchains is that a blockchain can use another blockchain, so one can develop a certain hierarchy in the system to develop a truly complex algorithms. For example, as I told you, let's consider the equation of states. To get a total energy of a scaled structure, we need to make sure that the charge density of the structure is converged. That's why equation of states does not use FLEUR calculation, for example, a single FLEUR calculation. It uses self-consistent blockchain to ensure that each energy that was obtained corresponds to the self-consistent field charge density. And that's also true for other blockchains. We have a set of magnetic blockchains. I will explain them later. And we also have geometry optimization blockchain. And yes, as you see, the self-consistent blockchain is the core of Aiida FLEUR plugin. We have several blockchains that currently unavailable that need to be updated for the recent version of Aiida, but I hope we'll have them soon. That are density of states blockchain and band blockchain. And as you see, I told you that self-consistent blockchain submits several FLEUR calculations, but you can find an interlayer between self-consistent blockchain and FLEUR calculation. What is it? It's an additional blockchain that wraps FLEUR calculation. It can submit a FLEUR calculation several times, and the main aim of this blockchain is to ensure the stability of your process of submission. Sometimes you get some technical error. Let's say, what if a supercomputer just gets stuck for a second and rejects to submit your work? Or what if you submitted a calculation and you realize that you have not enough RAM memory for the calculation? In this case, FLEUR calculation will fail, and this higher level blockchain on top of the FLEUR calculation make a decision how to fix this problem. For example, if it realizes that you have memory issues, you have not enough memory for your calculation, it will automatically increase the number of used resources by the factor of 2. And maybe in the next try, you will get enough the total memory. And for now, we have only simple scenarios how to fix this, and it will evolve in the future. And now let me proceed with the higher level blockchains. And during my talk, I will cover only magnetic blockchains. And the first blockchain that I'm going to consider is a magnetic anisotropy energy blockchain. Did you do magnetic anisotropy energy calculations yesterday? Yes? Did you have time, Daniel? Great. So, yeah, as you already know, energies of the system with different direction of spin alignment tend to have different energies. For example, we have different energy for this structure and this structure. And it's a pretty common task for our institute that people want to know what is the distribution of energy between different spin alignment for this one, this one, this one, this one, and this one. Does it look very similar? It's basically the same problem as an equation of states. One needs to submit a set of almost the same calculations with basically only one different parameter. And it can be done by hand, but it's frustrating to do it by hand. So that's why we develop a blockchain for this. This blockchain, similar to equation of state blockchain, can be initialized via initial structure and some parameters that we will consider in detail during the tutorials, and submits a self-consistent calculation for all spin alignments that you specified into the blockchain parameters. And we will end up in quite demanding task. It will, in this example, you will need to do at least 250 iterations with spin-orbit coupling. It can be computationally demanding. However, it will work and generate outputs. It works fine, but you probably did it yesterday. There is another way to estimate this value of magnetic anisotropy energy, is to use a force theorem. The force theorem blockchain first submits a reference calculation, as you probably did yesterday, for specific spin alignment or even without spin orbit coupling, converges it, obtains charge density, self-consistent charge density, and then it submits a single FLEUR iteration for each specified structures. So we basically can estimate the magnetic anisotropy energy distribution in a smaller amount of iterations. It will work faster, and we can obtain the outputs. And as you see, all of this should work automatically. You need to take care only of this part, initialization of the inputs, and how to control this behavior. It's supposed to be much simpler than doing it by hand, as we did yesterday. The other example is a spin spiral dispersion blockchain. Did you do it yesterday? Did you? Yeah, great. So, as you know, each of the structure have different energies for different Q vectors, and it's a common task for our institute not to study the difference in energies between two C structures, but to study the dispersion over the full Brillouin zone. And it's pretty similar to the magnetic anisotropy energy and equation of states. It can be done in two ways. First of all, we can converge to call self-consistent blockchain for all required Q vectors. And the second way is to use the force theorem. And it has pretty the same structure. Yeah, it's magnetic anisotropy energy and spin spiral dispersion are pretty the same. Both of them have a converge blockchain, which explicitly converges charge density for each specified Q vector. Will end up in a high demanding computational task. Or we can use the force theorem blockchain, which will first converge the charge density for a reference, and then using the initial charge density for the force theorem step, we can estimate the energy distribution in a faster and less demanding way. That's the end of the Aiida FLEUR presentation. And you can always find more information and more detailed description on our documentation page, which can be found on this site. And if you cannot find information that you might need, you can always write a new issue, contact us. We'll be happy to help you with any issue. And in the end of my presentation, let me make a small